small aqueous compartment because there's not a whole lot of space between these two membranes. But there is space. There is an aqueous compartment there. Okay, so the nature of that communication involves an electrical signal propagating along the wire that is the axon and being converted into something that can get across here, because you can't have a spark going across there. That's not the way it works. There has to be some sort of conversion, and what happens in the postsynaptic cell is that chemical communication gets converted back into another electrical process. So let's talk a little bit about the nature of that thing, type of communication just in general terms, and then go into the actual channels that do it. So if we go back to the notion of a electrode monitor set up here, and then we measure the activity at one particular region of the axon. But in this case, instead of talking about, X and Y moving along the axon, let's just talk about degrees of stimulation. Let's take a cell and we just sort of pet it gently, so that we gently stimulate, or maybe we shine dim light on it if we're talking about visual transduction. Anyway, some sort of relatively minor stimulation of the nerve cell in this region. Then you'll end up with an action potential, say, that looks like this. All right? And then, instead of having the gentle petting, you smack the end of the mechanosensor. So you give a massive stimulation to that region of the axon and measure the action potential. And what you'll get is a trace that looks like this. Okay? Meaning, the extent of the stimulation has no effect on the size of the action potential. And that's referred to as the amplitude, that how big this wave of polarization and hyperpolarization is its amplitude. And the answer is there is no effect on this amplitude. It's referred to as all or none. Either there's a resting potential or there's an action potential exactly like this that happens. The difference is how often it happens. So that if you've got the little detector and it makes a beep every time you see an action potential in this one region of the axon, then what will happen is when you pet gently, you'll get beep, 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 each one of those being a pulse. But if you smack it really hard, then it'll be beep, 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 beep. So there'll just be more action potentials per unit time, per second, in the case of the actively, strongly stimulated nerve. So we would refer to that as being frequency modulated, FM, just like Kicks 104 FM. Frequency modulated. It is the number of events that is used to determine the extent of the stimulus, not the size. How many, not how big. Okay? Frequency modulated. That's what the electrical communication is. But at the synapse, that information is converted into neurotransmitter release. And we'll talk about how that works specifically next time, probably, not today. But that process involves dumping neurotransmitter into the synapse. So in this case, the postsynaptic cell is actually measuring the concentration of neurotransmitter. It's figuring out how much. It doesn't care how fast the neurotransmitters get released or how slow they get released. It's measuring the absolute concentration. It's saying if there is 10 millimolar serotonin, that's threshold, boom. And if there's 9 millimolar serotonin, don't do anything, that kind of thing. It's an exaggeration, but that's kind of the way it works. So we would refer to the communication at the synapse as being AM, amplitude modulated. It's the size of the signal that it counts, not the frequency. Okay? So FM modulation counts for the electrical properties of nerves, amplitude modulation, the communication at the synapse. So what we have to do is establish how that can be done biologically, given the ingredients that are allowed in terms of macromolecules. Okay, and the way to do that is to think in terms of the nature of channels. How can you make these, how can you create this kind of pattern of activity given what we know about transport behavior, Eisenman, if you remember him, selectivity, things like that. let's do the action potential first. Our requirements are that it be mediatable. It can be done with two different types of channels, and only two: sodium channels, potassium channels. Somehow we've got to account for the fact that sodium channels open and close faster and bursts. Sodium channels are delayed, stay open longer, and we've got to account for the unidirectionality of the action potential. Why is it not a ripple? That is, why can you not stimulate in the middle of the axon and the action potential go in both directions? And I promise you, you can't. So the way that works is built into the structure and the mechanism of the sodium channels themselves, and it was predicted with 100% accuracy by Hodgkin and Huxley without any knowledge of what sodium channels look like experimentally. So what they did was come up with a model that has been remarkably successful since 1952 when it was originally published. So it bears describing specifically. And what they propose is that each of the important voltage-gated channels, the sodium channels and the potassium channels, can exist in three distinct states. Called resting, or R, open, or O, closed, or let's actually call this inactive. It's better. Only one of these three states actually allows an ion to get across. So I'll just keep it generic and call it a plus, because this can apply to the sodium channels, and does apply to sodium and potassium channels equally, these three states. So the resting state, that is the state of the channels, both sodium and potassium, when there is a resting potential in a neuron that has not been stimulated, would involve the inability to transmit ions across the membrane. And in the Hodgkin-Huxley model, they had some kind of gate that was distinct from the gate that is formed in the inactive state. And exactly how you draw it is not important. We'll actually do a little bit of the mechanics of it in 2013 terms, so I think it might reinforce this notion. But the idea is, however it's achieved structurally, there is something about this state that is different from this state, even though neither one of them can transmit ions across the membrane. Both of these have no ion permeability. The open state, on the other hand, does allow the transmission of ions across. So the way the action potential works is when a wave of depolarization comes in from the left, it encounters or is encountered by sodium channels in their resting state. And that wave of depolarization converts those resting ion channels into open ion channels, which means that a wave of depolarization increases the polarization as it moves to the right. So it's just kind of a compounding effect of the depolarization. This channel opens because the channels to the left of it opened a second ago. Okay? So sodium ions move across. But relatively quickly after that happens, the sodium channels enter into an inactive state. So even though the membrane is depolarized, there is no further movement of sodium ions across. And as a result of that, the pattern looks like this. The wave of depolarization is coming this way. That means that these channels were opened a minute ago. And as a result of that, they undergo the sequence from resting to open to inactive. So at this snapshot of the action potential, when we're looking at it right here, what that means is that if we think of this as an XY spatial arrangement, then the sodium channels here are inactive. They have undergone that third state. These channels are open as a result of the action potential having opened them up, and then the channels to the right of those that have not experienced the action potential yet, they are resting. So what happens is, this wave of depolarization does really only one thing. It activates these channels. The wave of depolarization is experienced by these channels, but they're inactive for other reasons. They cannot be activated by the depolarization. They're in a different state altogether. So now you have an explanation for why the action potential is unidirectional. It can only open channels to the right because of the obligatory arrangement resting, open, inactive. The inactive ones over here, once this wave of depolarization gets out to here somewhere, let's say, they go back into the resting state. So if we took a snapshot of this and then took another snapshot a few milliseconds later, then these channels would be resting, these would be inactive, and these would be open. Make sense? So that's the way that works. So it's that period of inactivity that accounts for the unidirectionality of it. And that state, or the fact that the ion channels can undergo that state, is referred to as the refractory period. And it's an obligatory component of voltage-gated ion channels that participate in the action potentials, because if they didn't have it, the whole system would not work. It would not be possible to propagate if you didn't have that refractory period.
So if we stimulate the middle of the axon, it only goes one direction?
It actually doesn't respond because of other things that I haven't talked about. There's no well, if you artificially, let's say you artificially depolarized in the middle of the axon, it would only go in one direction. All right, I'll take a couple minutes break and then we'll wrap up.